Hi. So at some point during one of the previous examples on graph sketching, the thought about odd and even functions came to mind, and I hesitated. I thought, do I really talk about it now during the video, or do I do a separate one? I thought I'll do a separate one. Okay. But odd and even functions, they're very useful to determine what the shape of a graph looks like. Okay. So here are the definitions. Okay. An even function satisfies this: f of negative x is f of x, and it's got the property that it's symmetrical about the y-axis. Okay. So if you know that a graph is going to be an even function, you can draw it quite quickly. Okay. And an odd function satisfies this property that f of negative x is negative f of x. Okay. And this one's got rotational symmetry about the origin. What I mean is you can rotate it pi radians about the origin and it maps back onto itself. Okay. It's no longer on the A-level syllabus. I don't know why, because it's quite useful. And sometimes I look at a function when I'm trying to sketch it, if I know already that it's an odd function or an even function, it makes it easier. Okay. Let me just give you some examples. Okay. So the first one, y equals x squared. Okay. So that's a parabola, as we know. Looks something a little bit like this. And you'll see straight away, you see it's symmetrical about the y-axis. Okay. And when you substitute in a negative value of x, you get the same output as when you put in the positive value of x. Okay. So x is negative 3, you square it, you get 9. X is 3, square it, you also get 9. Okay. And it's the same for any even powered function like that. So x squared, x to the 4, x to the 6. Okay, maybe that's why it's called an even function. I don't know. Okay, but if I drew the graph of x to the power of 4, it's the same as that. Maybe just a bit steeper. X to the power of 6, x to the power of 8, and so on. Okay, so that's quite a typical even function. Okay, let me show you just a few others, just as way of examples. Okay, the graph of y equals cos x. Okay. Easy one to draw because it's also symmetrical about the y-axis. Although when I do draw it, normally I just draw this bit here, you see, because usually we're interested in between 0 and 2 pi. Okay, but if I have to draw it on the other side, then I know it's going to do something like this. Let's just try and get the graph looking a bit right. So it's something like that. Okay, negative 2 pi. And let's just stand back to see how good that was or how bad it was. It'll do. Okay. Because as you know, when you put it in a negative value, for example, negative pi over 2, that's the same as when you do the positive angle, cos pi over 2. Okay, and that's something that's in the syllabus. Cos negative x is the same as cos x, but it's just not strictly defined like this. Okay, but this is an even function, which means it's got a line of symmetry about the y-axis. Okay, and I'll show you another one maybe. One that is just slightly different from that. So what's another one? If I just change that from cos x to the hyperbolic cosine, so y equals cos x, okay, obeys the same rule, okay, and here's the graph. It's called a catenary. Yeah, very good, well done. Okay, so it looks like a parabola, but it's not a parabola. That's a bit dodgy, isn't it, to be honest? So that's sometimes we're asked to prove that these are even functions. Okay, how do you go about proving? Well, with the x squared one, it's quite simple. Okay, because what you do with the x squared one, you just say f of x is equal to x squared. F of negative x is equal to negative x squared. Expand the bracket, same as x squared. Therefore, the same. Okay, how do you prove something like this? Maybe just think about it. You'd have to write out the definition. That is, you've got half e to the x plus e to the negative x. Okay, and what you do to prove it is you then work out f of negative x's. And so what that means is replacing x with negative x. So you have e to the negative x plus e to the negative x. And in a proof, you need to write that. You can't just miss that bit out. And then you'd have half e to the negative x plus e to the x. And maybe just write that up as half e to the x plus e to the negative x, which is the same as that. Okay, so they are set out the lines of working for you, showing you how you would actually prove that that is an even function. As long as you can prove that that and that are the same, then it's done. Okay. However, we're not really talking about proofs, are we? I'm just demonstrating what an even function actually looks like for the time being. Now, I've got written here on this board what the graph actually was that I was thinking about. Can you see that okay? Good. Yeah, so remember on one of the parametric equations we ended up with this, y equals x squared over 9, x to the 4 over 3 to the 4 minus 2. And at some point in the video, I think I said something like, it's got reflective symmetry about the y-axis. Okay. Basically, it's an even function. It's an even function because of the square term there and the power 4 term there. What that means is, period x is a negative value, you get the same value as positive. Okay, so that means that it is an even function. Okay. Now, that was quite crucial because that helped me decide what sort of stationary point that was. Okay, I instinctively knew the graph would not do this. No. Okay, I knew it wouldn't do that. Why doesn't it do that? Because then if you reflect it, the graph will then do this. Okay, and then that is what's called a cusp. Okay, it's not actually a continuous flowing curve at that point. The curve is not actually continuous there. If you look up the term continuous, it's actually a rather more complicated definition, but continuous basically means it's a smooth flowing curve, like that's smooth flowing. When it does this, like comes up to a point, it's called a cusp, it's not continuous anymore. Okay, and because this here is not the sort of function that would be discontinuous, is the term, I knew it wouldn't be doing that. Okay, so the only thing it could do, really, when looking at it, the only thing it could do reasonably was to come up to the origin there as if it was a maximum point and then be reflected like that. Okay, that's the only possibility really. Okay, so you could have deduced that without doing the calculus, you see, just by considering that was an even function. So another reason why even functions are kind of useful. Let's look at odd functions then. So typical examples of odd functions like y equals x cubed. Okay, so it looks something a bit like this. There we go. That's the graph of y equals x cubed. Okay, and as I said, it's got rotational symmetry about the origin. What that means is you can rotate that graph 180 degrees about the origin. Okay, maybe if I did it on my smaller board, I could have done it. I'm not about to pick that up and rotate it. Okay, and it's the same with the graph of y equals x to the 5, x to the 7, basically any odd power. Okay, and you can rotate it. Okay, even if you have x to the power of 1, because of course the graph of y equals x to the power of 1, which is the same as y equals x. Okay, it's a straight line with the gradient of 1. You can rotate that 180 degrees about the origin. Okay, and so knowing whether it's an odd function or not can actually be quite useful as well. Other examples of odd functions. This one here, y equals sine x, is an odd function. Okay, let's just do a quick sketch of sine x. So normally I draw it like this, you see, from 0 to 2 pi. And know that it's an odd function, it's going to do this, you see. If it's not brilliantly drawn. Oh, that's horrendous. You get the idea. Okay, you can rotate the whole graph 180 degrees about the origin, you see. It's just getting rid of that horrendous curve. It was not very nice, was it? Another one, the hyperbolic sign. So y equals sine x. You probably guessed that this one was coming up. Okay, so let's just sketch that one on this board here, shall we? Just so I can do the rotational thing. Okay, so if I just sketch it looking like this, here we go. It looks like a cubic graph, doesn't it? Do you remember that's the graph of sine x? Yeah. If I then just rotate it, you see? There we go. It's supposed to look exactly the same. Okay, that's what the rotational symmetry actually is. Okay. How would you prove that this is an odd function? Maybe just do that. So you'd set it out as f of x. Now with proof, yeah, you generally use the f of x notation, like I've done there. Okay, because when you're proving things, you've got to define it clearly as a function. Okay, as opposed to y equals something. Okay, and then you write out the definition of sine x, which is that, and then what you do is you'd write down what f of negative x is. Okay, so half of e to the negative x, subtract e to the negative of negative x, and then just write half e to the negative x, subtract e to the x. And then in order to have it looking the same as that, we've got to put negative outside the brackets. That'll be e to the x plus, oh no, ex subtract e to the negative x, and just check that that's the same, half e to the negative e to the x, that's that bit there, and then the negative times negative is positive, okay, and then that's the same as f of x, oh no it's not, it's the same as negative f of x, that's a bit, not very well done, okay. I mean written like that it's fine, you say oh yeah, it's perfect, yeah it is, but sorry, the explanation was a bit dodgy. Okay. But yeah, that's it. Yeah, because what you want to do, of course, is prove that f of negative x equals negative of f of x, and there it's done. Okay, because that is obviously the negative of that. That's how you show or prove that you've got an odd function. Okay, as I said, sometimes just knowing whether these are odd or even functions is quite useful. Okay. Just before we go along, not all functions fall in that category, of course. You know, like y equals natural log of x, y equals e to the x. Yeah, they're not odd or even functions, are they? Okay. Some of them, you might think they're a mixture. Okay. What would you think this is? Y equals tan x. Go. Odd or even, or neither? You can probably tell just by the graph it's not an even function, is it? Okay. But when you split it up as sine x over cos x, okay, sine x is an odd function, isn't it? And cos x is an even function. What do you think happens when you get an odd function divided by an even function? Again, think about it. You actually come out with an odd function. And you know what the tan graph looks like, don't you? Okay. Yeah, it's got this property here and this property here. Okay. Generally speaking, it's not proof, of course. Generally speaking, an odd function over an even function is an odd function. Okay. So sometimes when you've got a fraction, you can just look at things like that. Here's a really, really simple example. Okay, really, really simple. Okay, so x to the power of 7 over x to the power of 4. So that's an odd function divided by an even function, isn't it? Okay, and what's that the same as? That's the same as x to the power of 3, which is an odd function. Okay. Anyway, I thought I'd just put that in there as an extra video because I thought you might find some of the things I talked about useful. Okay.